In this example, a pendulum of mass m swings on a light string of length L. If the mass hanging directly down is set at the 0 point of gravitational potential energy, find the gravitational potential energy of the pendulum as a function of theta and the length of the string L. We know what our potential energy equation is for gravity, and that is equal to mgh. And h is the vertical height, right? So here's our initial point right here, and then here's our final point here. So we're looking for, well, we need this height h, but we need it in terms of the length of the string and that angle theta. And so what we can do here is draw a horizontal line from the current spot of the ball to the left. And what you can see here, if I can draw that straight, is that we made a triangle. So we made a triangle, and I'll go ahead and highlight that. So there's our triangle. And what we want to do here is use that triangle to write h in terms of L and theta. And so what we can do is notice that this length here is going to be the total length of the string minus that height. So this right here is L minus h. Okay, and what we can do then is say that the cosine of theta is that adjacent side, which in this case is L minus h, and we're going to divide that by the hypotenuse, L. And now we can solve for h. So if we do that, we're going to have L cosine theta is equal to L minus h, and that's going to give us h is equal to L minus L cosine of theta. And we can simplify that a little bit by factoring out the L and write it as 1 minus cosine theta. And then now all we have to do is sub that in for h, and we have potential due to gravity is equal to mg L 1 minus cosine theta. For the next example, we're going to be looking at number 19 in the Knight textbook problems. And so for 19, it says a particle has the potential energy shown in the figure. What is the x component of the force on the particle at x equals 1 meter and 4 meter? So they're giving us a graph of potential energy versus distance. And so in general, so potential and distance, I'm going to draw an arbitrary graph. Okay, so let's just say this is what our potential energy function looks like. Okay, so what we know from the last video is that potential energy, change of potential energy, is equal to, in terms of force, it is equal to, so if you're in honors physics, then it's negative F dotted with delta x. And if you're in AP physics, then it's the negative integral of f dotted with dx. Okay, and we said that force is equal to the negative derivative of potential with respect to x. And if you're in honors physics, you could say force is the negative change of potential with divided by delta x. So if we're given a potential energy function with x as the independent variable, and we want to know what the force is, we want to know what force is at some given x value, then what we can do is we can take the negative of the slope, right? Because this looks like a slope formula, and if you're in AP, you know that derivative basically means slope. Okay, so all we have to do is find the slope at whatever given value, right? So you could just draw a line tangent to that value. But if we look at the graph for number 19, the line is linear, so it shouldn't be a problem to find the slope of that line. So for 1 meter, you're finding the slope of that first line, actually the negative of it to get the force. So the force in this case is negative of the slope, and we can just do rise over run. So this is going to be negative 60 joules divided by 3 meter. And so we end up with a force of negative 20 joules per meter. And just to check here, let's make sure that joules per meter is equal to a Newton. So joules per meter, we know that 1 joule is equal to 1 Newton meter, and we're dividing by a meter, and the meter cancels out. So that works out. Okay, so now we just need to find the force for the force at position 4 meter, and that's going to be the negative of the slope again. And so that's going to be negative rise over run. In this case, the rise is negative 60. So now we're going to get a positive force. And the run in this case is going to be 2 meter. So we're going to get a positive 30 newtons. All right, this next example is just for AP. And we're going to look at number 20 for this next example. We have a particle moving along the y-axis, has potential energy of U equals 4y cubed joules, where y is in meter. So this is number 20. We have potential energy is equal to 4y cubed joules. Okay, and first thing we need to do is graph the potential energy from 0 to 2 meter. Go ahead and get our coordinate system here. And actually, before we start graphing those, let's go ahead and get some data, and we'll just get those. We'll just get a few points from 0 to 2 to get a graph for this. So we want to graph position on the x, potential on the y. And so let's get a few data points here. And so we'll do the potential energy at x equals 0. We'll do 0.5, 1, 1.5, and 2. And if we just plug those in, potential energy for, oh, this is y, sorry. We're using y, not x. So potential at position 0, we get 0. Okay, and so all we're doing is plugging those values into that equation to get the data points. So I'm going to skip to that point. So there's our data points. So for our y, we're just going to do increments of 0.5. Okay, and then our potential energy goes all the way up to 32. So we'll just say this is 30 here. So there's our coordinate system. And so now we'll go ahead and plug those values in. There's our graph, and now we just need to find the y component of the force on the particle at 0 meter, 1 meter, and 2 meter. So one way we could do this, just like before, we said force is the negative derivative of u with respect to, in this case, y. Okay, we could find the negative slope at each of those points. But since we know calculus, let's just go ahead and find the derivative. So force is the negative derivative of that function, so 4y cubed. And so the derivative of 4y cubed, that's going to be negative 12y squared. We can find the force at each of those points. So f of 0 is going to be 0. F of 1 is going to be negative 12 times 1 squared, which is negative 12 newtons. And then F of 2, that's going to be negative 12 times 2 squared. So that's going to be negative 12 times 4, so negative 48 newtons.